In this problem, what we're going to do is we're going to talk about finding half-life and creating a formula when we're given that we know a population decays exponentially and a couple of values. So we have a population, and I'm just doing very general. This can be applied to bacteria, carbon dating, a whole bunch of different scenarios. So it decays exponentially from 100 to 20 in 1 week, units, whatever those are, depending on what you're dealing with, grams, so on and so forth. So, number of bacteria in the population. So let's find it. What we're going to do is we're going to find its half-life and get a formula in terms of number of days. And so we're going to look at a way of solving this. So one way is I can think of 100 as my initial, and I know that there is going to be some rate of decay, and it actually doesn't matter which model you use, AB to the T or AE to the KT. So for this problem, I'm going to go ahead and use AB to the T. Gosh, I said it and forgot to write it. And so I've got 100B to the number of days, 7, equals 20. This is going to find my rate of decay in 7 days. So basically I solve this for B. So I divide both sides by 100. And so over here I get 1/5 or 0.2. So 1/5 equals B to the 7th. Now I don't need logs to solve this equation because I know the exponent. You only want to use logs when the unknown is in the exponent. So I take both sides to the 1/7, and so I get that B equals 1/5. I'm just going to write it as 0.2 now, to the 1/7. Well, let's think about why this makes sense. It's going from 100 to 20, so there's 20% left in 7 days. So 20% remaining in 7 days gives us our base. So we can actually make the model now. Now that we know B, we know that our model is going to look like y equals some initial amount times 0.2 to the T over 7, because we know it decays to 20% in 7 days. Now, we need to find the half-life. We don't need to know the initial, or we could start with 100 again. We're going to get the same thing. But we want to know when the initial of A gets down to half of that. So we want to know when it's down to 0.5A equals A times 0.2 to the T over 7. And we can cancel the A's out because we're going to divide both sides by A. And so we get 0.5 equals 0.2 to the T over 7. So here's where we'll employ logs or natural log, whatever you prefer. We're going to take the log of both sides, because now I can pull the exponent out front. So I have log of 0.5 equals T over 7 log of 0.2. We're almost there to getting our half-life. Our half-life is a time. So I'm going to multiply both sides by 7, so that's going to give me 7 log of 5 over here, and gets rid of it there. And then divide both sides by log of 0.2, and I've got my T. Now, this isn't very pretty right now, but this is something I can calculate in a calculator. So, doing so, let's go ahead and do that. We have 7 times log of 0.5 divided by log of 0.2, and we've got a half-life of about 3.0147 days. So just under half a week. Which makes sense because it's decaying exponentially. As it decays more, it's going to actually decay slower over time. So there's our half-life. and we had built our model earlier right here. Now if we know an initial amount, we can plug it in there. So that's how we can do those two given just a little bit of information.